Could I have somebody give me a definition they found for electric current? So this is all true, but there's like a quantitative way to describe it because you can have different currents. And I think the easiest way to understand this is the speed of charge. Speed of charge movement. So nice, I like all those definitions. And I hope you feel like you saw different currents when you started playing with potential differences and with resistance. What did y'all find for resistance? How much a circuit opposes current. So we now sort of see our three variables we have to consider when we're describing charges moving through a circuit. The potential difference, which we spent so much time last week talking about in the context of batteries, this is kind of how much the battery is pushing charges through. We've got resistance, which has to do with how if the circuit resists that movement of charge, fights it. And then we got current, which is how fast charge actually moves. So all three of those, I think, are visible when you do that sim. And that's one of the reasons we like that sim for describing these things. I want to talk real quick about the speed of charge moving, because that's a concept you guys are good at, but it's hiding a little bit, and sometimes you can miss that this is something you understand. So let's talk about velocities or speeds we studied so far. So the first one you studied was kind of the speed of distance. It sounds really silly, because most people just call it a speed. But what was my equation for velocity? Yeah, change in distance over change in time. So you could call that how fast does position change? I am 1,000% confident in y'all's ability to understand velocities. You've shown that to me. It's honestly stuff you knew before you ever got in this class. There are two other speeds that we study this year. Current is one of them. The other one we studied about a month ago. And I think students would be very good about this if we didn't make it more confusing than we had to. Does anyone remember what we call the speed of energy charges? This one is actually power. So we usually called it P. Here. What's a joules per second? It's a change in energy over a change in time. So if you're going to put that in words, how fast does energy change? So we studied this. You had a take-home lab where you ran up the staircase, and then you walked up the staircase. And you acquired the same amount of energy both times. Your delta E was the same. But when you did it faster, you had more power. I think at the end of the day, we would understand power much better if we just called it a joule per second. Because all the work you guys did learning velocities and figuring out distances from them, that applies here. For example, how much energy do you use? You multiply power times time. Just like how far do you go? You multiply velocity times time. So we're kind of getting into this territory now when we talk about the speed of charge. And this is current. What do you guys think a nice letter for current would be? That would be great. I'll tell you what's a really crappy letter, but the one we're going to use is I. It stands for I don't know why we use this letter. And current is going to be just like velocity was the change in distance over the change in time, power is the change in energy over the change in time. Current is going to be the change in charge over the change in time. And this is how fast does charge move. All right, we'll talk about the actual unit for current in a second. But let's try to go by analogy here. Meters per second, joules per second. This is going to be something per second. It is the coulomb. But once again, we have to name this after a dead guy. So this is called the ampere. So the unit is amperes, which are really coulombs per second. But almost every person you'll ever meet calls this an amp. You're going to build me these 4 series circuits, and you're going to get the current through each object, either the battery or the resistor, and you're going to get the potential difference across it. These are series circuits. The current basically has to pass through everything. And you can think of electric current as being like a lunch line. Every electron is bumping up against other electrons. If it's going to move, it's not getting faster in one place and not speeding up in another place. If the kid in the back of the lunch line tries to go faster than the people in front of them, people get knocked over. So we only have one current throughout this single path. So all of these are going to get the exact same current. So you just have to find it in one place. Potential difference, basically just touch the 2 leads of a voltmeter across whatever it's asking you to measure. So for the total, you always touch across the battery. And then for each individual resistor, you just touch across 3. So ultimately, what I would like to see is I would like to see how this current is related to total resistance. So just really briefly, I'm guessing that you saw 9-volt potential difference across the battery and a current of 0.9 amps. I think you saw the 2 resistors having to share the total 9 volts, but still only one current throughout everything, which was 0.45, is that right? So in the 3 resistor circuit, you still had a total of 9 volts, but each of them got 3. And the current was 0.3. And again, these currents are all the same because there's only one place for charges to flow, and they have to wait for it to turn them on. And then here we had to share okay. So the pattern I want you all to see is that the more resistors you add, the less current. We have to think about how these resistors are adding together. I like to think of resistors as being like a traffic. So let's say you're trying to get from here to New York City on 95. If you've ever done that, it's not much fun because there's usually several places where traffic is slowed down. And each one of them messes up the total traffic. So if we only have one traffic jam between Bridgeport and New York, we're doing pretty good. But if we have 2 traffic jams, their cumulative effect is more. If we have 4 traffic jams, man, overall traffic's not going to flow. So you can take resistors in a series circuit and you can add the resistances together to get a total. So our total here is only 10 ohms. But here we have 10 plus 10, so this is 20 ohms. This is 30 ohms, and that's 40 ohms. 10 plus 10, 10 plus 10 plus 10, 10 plus 10 plus 10 plus 10. We're getting a total resistance. It's getting more and more. So that's what I would like you to graph in number 7. I want you to make a graph that has current in amps on the y-axis and resistance in ohms on the x. And you're going to get the resistances by using the total. So as we look at our graphs, notice I drew a best fit line on this one. I used a ruler. And honestly, since this is simulated data, not surprisingly, the points all fall right along a line. So go ahead and do that with your ruler. You can't do that for this one because this is not a linear graph. So don't ever make a best fit line if it's not linear. That's not something we can do by hand. What we're going to try to do with these two graphs is we're going to try to generate equations from them. Because what we need to do is what George Simon Ohm did. We need to come up with an equation that relates current and potential difference and resistance. So let's start with the top one. If you want to make it a little more clear, you can take your pencil and draw like a smooth curve that goes as close to as many points as possible. So I didn't do a great job there because I hit something underneath. But let's try to figure out what could have this shape. So let's start with a sentence. I think this can help. As resistance gets bigger, current gets smaller. Awesome. So if you were going to try to think of a mathematical way to describe this using the word proportional, what kind of proportionality does that sound like? Absolutely, this is inversely proportional. So that suggests that the appropriate curve to draw would be the inverse curve. So something like this. You know, that's the one that goes like this, and then it goes like that under the x-axis. But we're only looking at the first quadrant here, so we're not seeing really. Now, honestly, it doesn't just have to be y equals 1 over x. It can be y equals 2 over x, y equals 15 over x, y equals 133 over x. It can be any sort of constant on top. So typically, we would write that as y equals a constant k over x. There's only one other little tweak to make to our graph. We didn't have a y-axis. We had a current axis. So current is some number k divided by the resistance. And that's the mathematical way of writing this. As resistance gets bigger, current gets smaller. Does that seem legit? So how about this graph? Well, let's write our sentence to describe it. As potential difference gets bigger. So what kind of proportionality is that? Absolutely, thank you. Directly proportional. So obviously, what shape graph is this? Perfect. So let's try to customize this one for our data. We don't have an intercept. So y equals mx plus 0, which is y equals mx. And Honestly, the letter M in physics don't go well together because M always means mass. So I'm just going to slightly change that. Y equals kx or some number. 2 or 3 or 12 or 148, whatever. And then, of course, we didn't have a y-axis. We had a current axis. We have an x-axis. We had a potential difference axis. So I equals k delta v. So these two big ideas together are the big ideas of Ohm's law, the thing that George Simon Ohm found. Current inversely depends on resistance. I think it makes sense. If the circuit elements fight the flow of charge more, charge doesn't flow as well. It's directly proportional to potential difference. If there's more of a push and a pull on the positive and negative ends of the battery, current flows more. The two Ks, we don't know what they are. They're just numbers. Let's call that K2 and this one K1. And now, let's try to figure out what Ohm's law actually is. So I'm just going to copy down our two equations that we got. So we have I is K1 over R. And we also have current is K2 times potential difference. So you could combine these into one master equation. It's got current on this side. It's got potential difference on top and resistance on the bottom. And what about the Ks? Well, they would all be combined together into some other number, K3. And that becomes the equation we can use to relate these three variables. Now, it gets a little easier than this. If we use SI units, resistance for a lot of circuits, and definitely the one that we're looking at, resistance here is a constant too. So the units we can use for resistance, if we pick them right, and we use amps and volts, these constants just turn into 1. So we define the ohm, the unit of resistance, so that this last constant ends up being just 1. And that gives us the simplified equation. Current is potential difference over resistance. This is what we call Ohm's law. It's often something that's familiar to students because it has a little bit to do with Newton's second law, which is kind of in the master equation for this class. So we spent most of first semester working with this one. And if you understand the logic here, you'll understand the logic here a little better. So we saw that objects accelerate more if you push them harder, and they accelerate less if they have more inertia, if they're harder to push. Ohm's law is not that different. We get more current, charge flows faster if we have more potential difference, if each charges carry more energy, if we push it more. And we get less if the circuit resists current more. They're not exactly the same, but the logic here can help with it. Usually we wrote this as sigma F equals MA. We just rearranged it. And usually we'll write this as delta V equals IR. Now we have a graph we could use to see if it's really valid to say we can ignore the constants. This graph has a slope that we can calculate, and it's worth doing that. Because if we take this equation, we can start to ask ourselves, we know it's linear, we can start to ask ourselves, what should the slope be? So I'm just going to make one tiny little change. Does anyone not agree that these two equations mean the same thing? We just kind of pulled out the 1 over r. If you multiply them back together, you get this. So why would I do that? Because if I line this up next to our equation for a line, we know on that graph I put potential difference on the x-axis, and I put current on the y-axis. So what's the slope? It's whatever is left over. So the slope ought to be 1 over the resistance. So we should find this slope and see if it is 1 over the resistance. And just for the record, the resistance was 10 ohms. So if we get a 1/10 as our slope, then we should be good. So a slope of 0.1 would tell me that this equation is valid and I can ignore the constant. So let's see. When you're getting the slope, you should pick 2 points. 0, 0 looks nice. It's hitting that directly. That one looks kind of nice. So 0, 0, and 3.5, comma, 0.35. I think you guys can see that that is going to give me the slope I want, but let's do it just in case. And that's 0.1. All right, so this equation is valid. So now we can use this equation, or its cousin. And the last part of what I'm going to have people do today is take these circuits. Notice these are not series circuits. They're parallel circuits. In other words, a charge passing through this resistor can do a complete loop without going through the other resistor. Similarly here. So your values are going to be kind of different. Once you get to 12 and 13, it's going to ask you to use Ohm's law. With the series circuits from number 5 and the new parallel circuits in number 12, it's going to ask you to solve for total resistance. So total resistance would be delta V total over I total. You're going to see stuff that's not very surprising for the series. You might be a little shocked by the parallel. But at the end of the day, when we have more resistors in series, the resistance seems to increase. That, I think, makes sense if you use the traffic analogy, that having more construction zones after each other slows down traffic more and more. What's surprising is that when we do things in parallel, it's not the case. Adding more resistors in parallel seems to drop the resistance. which is mu.